Hello there. This is the final summary lecture of the course Transmission Electron Microscopy, Theory of Imaging to Advanced Applications. This has been a course of over 25 odd hours with close to 35 to 40 lectures, where you've seen various modes and principles of operation of transmission electron microscopy. There have been a few demonstration sessions on how the experiments are done. And also, we've seen how the images look like and how do you interpret them. So in this 1.5 hour or 2 hour lecture, what I'd like to do is have a recap of what we've learned in this course, not going into complete details, but highlighting the brief concepts and try to understand what TEM is used for and what are the kind of results that you get from doing such an analysis and how is it useful for not just material science, but for applications across various fields. Before I go further into this lecture, I'd first like to acknowledge the contributions of a few people. Primarily, I started learning TEM at TU Delft. I'd like to thank Dr. Chang Su and Franz Tichler, who trained me on the microscope, and of course my PhD supervisor, Professor Henny Zandbergen. Working there has given me immense exposure to try out various things and learn about techniques on TEM. And then I spent some time at Forschungszentrum Jülich. Dr. Govind, he's one of my first PhD students who's in Forschungszentrum Jülich now, and my collaborators, Dr. Amir Tawabi and Professor Rafael Dunen-Borkowski. Collaborating with Jülich has widened my scope and understanding in transmission electron microscopy, and I think anyone who's connected to TEM should actually visit this center because it's an amazing place, and the developments at the forefront of electron microscopy are largely tested in a few labs, and this is one among them. Few others being at the Lawrence Berkeley lab and some of the national labs in the United States. But this is a place where everyone should certainly visit and get an exposure to. Then my student, Mr. Sriharsha, who's been patient with me and helping editing and populating the content for this course. He served as a TA for this course. And the discussions with Dr. Tetsuo Oikawa at GEOL, he's also very friendly and extremely helpful and very knowledgeable in the area of transmission electron microscopy. Discussions with him have always been inspirational, and they give you a simplistic view of quite difficult problems. And of course, the team at IIT Hyderabad and the NPTEL team, I'd first like to acknowledge the support of NPTEL for taking the initiative to organize this course, and Mr. Vijay Bhargav and Mr. Purnachandar from our Center for Continuing Education at IIT Hyderabad, who've played an immense support role in getting the content to this course curated. They've been available round the clock, and their support is something which we really acknowledge. And some important information for those who've done this course and reached this far. I've primarily followed the books shown here, the book by Rolf Erni, and then the text by Tanaka, and of course Williams and Carter, the most famous book on transmission electron microscopy. A few journal articles, especially when I was discussing on aberration correction and high resolution electron microscopy, I followed these classic papers. And also, I'd like to mention some of the monographs on advanced reading content from the texts in Progress in Material Science, Progress in Electron Optics. These are quite interesting and elaborate texts which give you a good perspective on how the technique is developed. And of course, some of the technical workshop or resources which are available, Professor Christoph Koch's website, his software that is built for learning TEM simulation, and also the texts and presentations available on CEO's website, which not just give you a perspective on aberration correctors and also their energy filtering systems and so on, but complete microscopy theory in general. And there are a few more web resources which I've indicated here. So let's recap what we've learned in this course. We started with defining what microscope is. The simplest microscope, of course, is a magnifying lens. And then we've drawn parallels between simple stereo microscopes and compound microscopes and transmission electron microscope. So let me show you the image of a stereo microscope here. So this is a simple stereo microscope. So you have an objective lens, you place the object, and when light is incident on the sample, due to the interaction with the sample, which is reflection in this case, you start seeing whatever is visible and the image is formed and you record it over here. So you can see the image here and you can record it on the CCD camera which is on top. If I look at a compound microscope, here is a compound microscope which consists of a condenser lens here, the objective lens here, the condenser lens is on the bottom in this case, and there is a specimen stage. But more importantly, when you are operating this in transmission mode, that is when you are using transparent specimens, and if I turn this upside down, so if the source here is on the bottom, but if I visualize this by turning it upside down and I draw a comparison with electron microscope, the source here is at the top and it is indicated by the number 1. So here you have your electron source, which is typically called as an electron gun, and in this particular microscope you see here, it is actually a lanthanum hexaboride gun or a thermionic emitter, and the objective lens is the heart of the microscope. The objective lens is over here and the stage here is coinciding with this location here. You have the illumination lenses, and I have indicated the objective lens on the optical microscope on the left. In TEMs, actually you are stacking lenses one on top of the other. So you have the condenser lens, the objective lens and the illumination lens or projection lenses combined together. But if I draw a parallel, the optical microscope, it is a physical glass lens and the specimen is placed on a stage, and the focusing here is done by moving the specimen up and down physically. Whereas in a transmission electron microscope, you can correct the specimen height physically by moving the specimen holder, which is indicated with the arrow here, through the goniometer here. But the lens here is actually a field lens, and by changing the strength of the lens, you are kind of changing the focus in the transmission electron microscope. And next we have the detection system. You typically use a CCD camera. You can see the image formed on the fluorescent screen here, which is behind this number 4. The fluorescent screen is somewhere here, and then the on-axis or off-axis recording cameras are below the microscope column. So this is the general layout of the microscope, and then we started understanding each of the components one by one in this kind of a sequence, the way in which they are arranged in a classical upright transmission electron microscope. Now if you look at where the TEM is used for and what do you use TEMs for, you can use TEMs for imaging, for measuring, for modeling, for manipulating matter on all kinds of materials. When I say imaging, the microscopes can be operated in various modes. It is conventional, classical, bright field and dark field imaging, and then you have diffraction, and then you have something else called STEM and high resolution imaging. And with all this, you get the microstructural and morphological information from a specimen. When I say measuring, the crystal structural information, microstructural information, and also whatever compositional information you get by combining with complementary analytical techniques, you get to know the information from the specimen. And by combining the imaging and the measuring and analytical techniques that you use, you build some information on the structure property relationships between a material. So this is where your modeling aspects come in. There is of course something called as crystal structure modeling, and also solving the structure or atomic structure of a material through focus exit wave reconstruction. And there is a lot of modeling done to even model the imaging and the contrast mechanisms in a material as well. So there are various aspects of modeling in connection with TEM. When I talk about manipulating matter through in situ experiments, now you can actually use TEMs as a labs just beyond conventional tools, and there's a lot of real-time experimentation that you can do where you see while the changes are happening in a material, you can record information down to the atomic level. In addition, you can also use transmission electron microscope like a tool where you can form structures and change the physical properties of materials by introducing defects or creating band gaps, and this is also a very interesting area. You can in principle study all kinds of materials provided you prepare the specimen which fits into the microscope, and if it doesn't harm the operation of the microscope vacuum and it is stable under the electron beam. So with all these, if you look at the limitations of the technique, primarily you are limited with the sample size. You are looking at a very small portion of a material. So the typical volume of a conventional 3 millimeter disc specimen is lower than 0.05 millimeter cube, and assuming the thickness of a specimen here is around 100 to 150 microns. In such a small specimen, the electron transparent region might be even smaller, so the information you get is highly localized. In such a scenario, understanding a material from various complementary techniques and building a bigger picture with bulk characterization techniques is always imperative, and it is important. The next thing is, transmission electron microscopes have the projection limitation problem. That is, after the electron beam interacts with the specimen, whatever is the information that is forward scattered is projected onto the screen or your camera. So what you're actually recording is a two-dimensional amplitude distribution of a three-dimensional specimen. So you're always limited to know where the features that you see are actually located across the thickness of the specimen. There is no depth information. The information is averaged through the thickness. So you need to have complementary tomography kind of techniques which give you three-dimensional information of a material. Then specimen preparation is actually a big challenge. Any material that was shown on the previous slide, you have to prepare it carefully such that you do not lose out the primary information from the material, and it has to be electron transparent. When I say electron transparent, it is really thin. Typically for an inorganic material, it is less than or equal to 100 nanometers across the viewing direction. The common terminology that you should not confuse with is a sample is typically a bulk sample, and when I say specimen, by using suitable preparation techniques, you thin it down such that it is ready for loading in a TEM holder, and the thickness along the viewing direction is certainly within the electron transparent regime. Then you have the problem of radiation damage. It affects largely organics, ceramics, minerals, and in some cases even metallic samples. As an example, the radiation damage increases with accelerating voltage, and quartz is one of the cases where the threshold for beam damage is at around 125 kilovolt. For carbon, it is 86 kilo electron volt, and so on. So you can mitigate the radiation damage by using suitable low dose techniques. There are cryo techniques. You can use fast cameras and sensitive detectors to get information of a material before you lose out the material under the electron beam. If you look at the present trends in electron microscopy, there is a lot happening. Classically, aberration correction has been one of the recent breakthroughs in TEM. By breakthrough, I mean this is already now close to 20 years. I think in 1997, the first successful experimental demonstration of aberration corrected TEM was done, and we crossed the 1 angstrom barrier. So with aberration correction, the resolution is no longer a hurdle. It's more or less become the baseline for advancing the technique of transmission electron microscopy. Here is a table which summarizes the ongoing trends as we discussed today in the year of 2026. There is lots of advancement happening in advanced detection and low dose imaging. We have more faster sensitive detectors which are enabling low dose imaging. There's also ultra fast imaging technique connected to microscope where you're looking at dynamic and beam sensitive samples. There's something I've classified as computational TEM because once you retrieve the projected potential and the information from a specimen, you can use a lot of phase reconstruction and specimen reconstruction information retrieval techniques such as 4D STEM, tachography and tomography to provide richer multidimensional data. Typically, you are using this for strain and phase. When I say phase here, please don't get confused with the metallurgical phase. It is actually the phase of the electron wave, and phase in turn is related to the electrostatic and magnetic potential from the specimen. You also have three-dimensional analysis, so this helps you overcome the projection limitation in a transmission electron microscope. Then we also have advancements happening in cryogenic and sensitive sample TEM. There are cryo-based methods that are being developed largely for biological materials, but also for a lot of functional materials where you have interesting properties close to the 4 Kelvin or even lower liquid helium temperatures. So there is a lot of advancement happening in this direction as well. Then in situ and operando TEM, you're trying to image the specimen under real-time working conditions. You get dynamic information from the material. This is a field which has been around since the advent of the microscopy, and there have been some in situ studies already explored in the mid 1970s or slightly earlier as well, where people were trying to have some kind of a stimulus onto a specimen and look at how changes happen. This area has got more and more interest, and with the advent of MEMS based devices and by enabling holder based in situ stimuli, the area of in situ microscopy has expanded a lot, and you can see many interesting dynamic processes in materials. Then there is specialized and multimode TEM, like I was mentioning, ultra fast, Lorentz microscopy and spectroscopy integrated TEM capabilities. In fact, there are 5 new state-of-the-art microscopes which are not commercially available being developed at the Ernst Ruska Center, where you are trying to combine more than one technique and integrating it into the TEM. For example, atom probe with TEM is one of the things, and then a high vacuum system with spectroscopy capabilities, an ultra fast microscope, and also a system which is connected to a vacuum system where you can deposit and grow materials on a two-dimensional substrate. So there is a lot happening in this particular area. And like the progress in many fields with the intervention of AI and ML, there is a lot of AI and automation which is used to improve the acquisition and analysis. In fact, some of the commercial microscopes now are already having AI-based detection and also orientation tools which are integrated into the microscopes nowadays. And then the most important thing, specimen preparation is extremely important to get good information from TEM. I would say more than 30% or perhaps even more success of a TEM measurement depends on how good the specimen is. There are lots of advancements happening with focused ion beam like the plasma FIB, cryofib, and also transfer methods to enable studying more and more difficult specimens which were not possible quite some time ago. Also, reducing the artifacts while you're preparing specimens becomes an important area. And furthermore, there's a lot of interest with the thriving areas of semiconductor, quantum materials, batteries, catalysis, and soft matter. A lot of work is happening in this area, which is combining more than one of the techniques mentioned above to get meaningful information from a material. So let us look at now the construction of a microscope and recollect some of the concepts that we learned through the course. Here is how the microscope layout looks like, and here is your ray diagram or a schematic of the microscope shown here. There are series of condenser, objective, projection lenses, and you have several deflection coils. Typically these are dipoles, or in some cases you have quadrupoles. By using various configurations within the microscope, you can actually illuminate the specimen in either parallel mode or by forming a probe, and with this there are various techniques with which you get a lot of information from a specimen. We'll start by recollecting what we saw with respect to electron sources and why these are important. So when I look at the electron source, it looks like this. The zoomed inset shows you the gun here, which is a thermionic emitter, and typically the electron sources can be classified as either field emission guns or thermionic sources. Within the field emission guns, you also have the Schottky field emitter or you have the cold field emitter. Typically, the source here in a field emission gun is a tungsten needle, whereas in a thermionic source, you have a tungsten filament on top of which you have a lanthanum hexaboride crystal sitting on the top. Now, the difference between a thermionic source and a field emission gun is the construction of a thermionic source is very simple and similar to that of an incandescent bulb. You do not need extremely high vacuum to run a thermionic emitter. So most common, easy to use microscopes for low voltage imaging and all typically rely on thermionic sources, also where you need high throughput imaging. And what happens here is when you start applying a current through a tungsten filament and which has a lanthanum hexaboride crystal sitting on top of it, by overcoming the work function barrier, you are actually allowing electrons to be ejected through the system. And then you have the Venelt grid, which focuses the electrons that are diverging to a spot, and this goes through your condenser lens and you form a probe, or you can spread the probe to form a sort of a parallel beam to illuminate the specimen. If I look at a field emission gun, the construction is slightly different because you have an anode, you have actually a double anode, one of which is useful to extract and the other anode also acts to lower the work function barrier, and this helps you with what is called as Schottky field emission. And by lowering the work function barrier, you kind of have emission, and the presence of the dual anode kind of a construction makes you converge the beam to a very sharp spot, and this becomes the source for the condenser lenses which are below the electron source. So with this, you actually have extremely coherent source with a field emission gun. Then if you bring the anode really close to the needle, and you can improve the vacuum even further. So in comparison with the thermionic source, the field emission gun needs to be operated in ultra high vacuum, and if it is even more stable and the anode is brought really close to the fine tungsten needle, you have the emission of electrons by not overcoming the work function barrier but by tunneling through the barrier. And in this case, you have the emission happening at low temperatures, and this is called as cold field emission. So I'll give you an example of how a thermionic emitter and a cold field emission looks like. So the video on the left shows you the source, which is a thermionic emitter. When I converge and spread the electron beam by changing intensity on the microscope, you can see that the point of convergence is rather large. And if I compare it with a cold field emitter source, the point of convergence is rather sharp. This gives you an example of how good the coherency is when you compare a thermionic emitter versus a cold field emitter. But there are a few important characteristics of a source which determine the quality of your imaging in a transmission electron microscope, and we'll look at them in the next slide. So if you look at what does the source influence in a microscope, firstly it is the coherency. Within coherency, you have two kinds of coherency. One is the temporal coherency and the other one is spatial coherency. By temporal coherence, you mean the electrons emitted from the source all have more or less the same voltage. So this means the energy of the electrons is, in practical cases, you would have approximately around 50 eV difference, which in turn changes your wavelength. But by combining with monochromator and also switching to a field emitter, the coherency is significantly improved, and you also have the monochromatic sort of an illumination that is possible. If you look at spatial coherency, what you mean here is all the emitted electrons come from a single sharp point from the source, and a combination of these spatial and temporal coherency significantly affects the resolution of your microscope. In particular, when you're imaging in STEM mode, the spatial coherence plays an important role and temporal coherence plays an important role when you're trying to do analytical TEM analysis. Then we have the stability of the source. There is something called as the source current stability. In thermionic emitters, you can actually switch on the source and then shut down the source after operation, and multiple cycles of this turning on and turning off still doesn't damage your filament or the lanthanum hexaboride crystal. The thermionic emitters are stable but have poor coherence. So we have the Schottky field emitter, which is once switched on, you do not switch on and it keeps running for a period of 1.5 to 2 years or even longer in a few cases if it is maintained well. And to lower the work function barrier, the tungsten needle is typically coated with zirconium oxide, and typically these have a stability of around 1% per hour. But when you look at cold field emitters, on an average, the emission current actually drops by about 5% per hour to even as high as 15% per hour. And what actually happens is, to improve the stability of these cold field emitters, you maintain ultra high vacuum, but when the source current drops below 25% of the anticipated or the expected source current, you do something called as flashing. And in the modern day microscopes, with the feedback control and the digitization of the electronic boards and so on, you can actually do this flashing reasonably quickly, and it is automated, so it makes life easier. In the very old days, thermionic emitters and the Schottky field emission guns were considered more practical and more stable, but nowadays, with the excellent temporal coherency and reasonably good brightness of the cold field emitters, they are used more and more often. Next, we have the brightness, which actually, when I say brightness, it is not how bright some feature looks like. Brightness is actually the flux of electrons that are emitted from the source, and it is measured over a solid angle. Brightness is having a unit of current per area or current per area per solid angle, whereas intensity is once this bright electrons are emitted from the source, when they are incident on the specimen and when they are incident on the screen, it is the intensity that you record on the screen, how bright or how dark it appears. And there is a small difference between brightness and intensity. Brightness is very critical for convergent probe methods, especially in analytical electron microscopy and STEM. So this is what you have with regard to electron sources, and they directly influence the quality of imaging and the resolution of images that you get in a TEM. Moving further, if you look at the electron lenses, almost all lenses used in electron microscopes are sort of round electromagnetic lenses, which are more or less converging lenses. If I understand how the magnetic fields look like and how the construction of a lens looks like, I'll show you this. You have a radial field. Typically, the radial component of the field is reasonably smaller in comparison with the Z component of the field. This is along the direction of the electron beam and the electron microscope. So the source is on the top and the beam traverses in this vertical direction downwards. There are a few manufacturers who use it the other way around, where the source is on the bottom and the detectors are on the top. That is with the neon and the test scan systems. So the radial component of the magnetic field is significantly smaller in comparison with the vertical component, and what this does is you can actually use what is called as a paraxial ray approximation. So if you look at how the fields are inside an electromagnetic lens, if you can think of the electromagnetic lens analogous to a solenoid, if you think of a current carrying conductor through which current is this way, the magnetic field then is So if the direction is here, the magnetic field is downward, and when a charged particle, that is an electron, enters this kind of a field, it experiences the Lorentz force and it follows a helical path. In some of the older microscopes, you would see the effects of this helical path influencing the image that you record, and you had the image rotation. The newer microscopes, because the electron beam trajectory is reasonably well understood, they compensate for this image rotation, and your image that you record remains stable with various magnifications. So this is how an electron beam moves in an electromagnetic lens. And if I look at the schematic construction of these lenses, typically these are water cooled lenses with a soft ferromagnetic pole piece, typically iron, and the coils are highly conductive pure copper coils which are wound, and when a current goes through this, you are applying a magnetic field along the vertical direction. By lowering the pole piece gap, you are kind of minimizing the aberrations that are caused in these kind of lenses due to the diverging magnetic fields. And the image you see here is a construction. The image on the left, or the schematic on the left, is kind of an immersion lens which was used in conventional high voltage microscopes. If you look at the image, this is from the text from Williams and Carter. The pole pieces look like this, and they are placed in here, and in front of the pole pieces you have sort of a diverging field. So these kind of lenses and the construction and the diverging fields actually cause some distortions, which in turn give you strong astigmatism, which is detrimental to the resolution that you can achieve in electron microscopes. If you look at the modern day microscopes, they typically use something called as a split pole piece kind of a lens. So we have a side entry holder, and when your construction is this way, where the pole piece is separated, initially when we were trying to achieve higher and higher resolutions, more and more immersion kind of lenses were only constructed which used a top entry holder. But nowadays you use a side entry holder with a split pole piece lens, and an example from one of our microscopes is shown you here. This is from one of the side ports of the Geol F200 microscope, and this is how your pole piece looks like for a high resolution pole piece for your objective lens. And the holder, when inserted, comes in somewhere in this gap, and it is not a physical lens but a field lens. And when you have such a field, you naturally have lot of diverging fields, and in turn you have the lens defects. So if I look at what are these lens defects, primarily it is astigmatism. What are lens defects for classic optical lenses? When all your rays that are passing through the lens do not converge to a single point, they form a disk of confusion. In fact, we have looked at this in good detail in our lectures on aberration correction. We will look at it once again when we revisit the summary of aberration correction a little later. But if I think of a sphere that can be fit in this particular region here, or a spheroid, the diameter of this is proportional to the third order of the azimuthal angle here. So are lenses perfect? The answer is no. Especially the electromagnetic lenses are extremely poor in quality when I draw an analog with the optical lenses. For example, when you look at the text in Williams and Carter, they compare the quality of an electromagnetic lens to the bottom of a soda bottle. So if you have a high quality optical lens versus the bottom of a soda bottle, you can see how aberrated this is, and that is how poor in comparison the electromagnetic lenses are. The origin of these defects is, of course, the diverging fields, and there are various other factors related to the stability of the electromagnetic lenses and the high tension and all the components involved in the electron microscope. Anything that can cause an electromagnetic interference and anything that can cause an instability to any of the electron microscope would actually give you some kind of lens defects. So how can we make them near perfect? This is what we have now, with the advent of aberration correctors, you are trying to minimize the spherical and chromatic aberrations, and also to an order the higher orders of astigmatism as well. And what effects do these defects have? With these kind of lens defects, you would actually deviate far away from the ideally achievable resolution when you're using an electron beam. And because of these many defects, and also having the electron beam closely concentrated along the optic axis of the microscope, and also you have the sort of paraxial ray approximation in transmission electron microscopes, we use largely apertures and diaphragms which kind of cut the higher order deviations of the electron beam to get the best quality beam as close as possible to the optic axis of the microscope. And as a result, you are actually using these kind of apertures which are limiting diaphragms, and they restrict the convergence angle or the collection angle, and they help you improve the quality of imaging. If I look at how the aperture holder typically looks like for a microscope, it is this. You turn the knob here and you insert the aperture of different sizes, and nowadays through these aperture holders you are also putting in MEMS based apertures which are electronically programmable and controlled, and you can use them as faceplates to alter the electron beam, and there are different locations where you can place these, and there's a lot that you can do with modifying your imaging system. So if you then look at what we covered on detectors and recording systems, here is an example of one of our microscopes where you see both the fluorescent screen and the recording system, which is a CCD camera. Nowadays you have direct electron detectors, CMOS cameras and so on, and there is a lot of advancement happening in this particular area. And depending on the application and the kind of specimens you study, you configure it with a camera which is useful in obtaining the appropriate dynamic range to record an image. Next, we have seen the construction of the electron microscope now, and if you recollect the specimen preparation techniques, we will recollect what kind of samples have we mentioned that you can study in an electron microscope, and how do we prepare them. Typically, all kinds of materials can be studied provided you prepare them carefully and you ensure that they are electron transparent, and more importantly, they do not affect the microscope when you insert this through a specimen holder in the microscope column. As long as you take the appropriate precautions, only then you can start investigating these kind of specimens. So if you look at the common specimen preparation methods for metallic samples, we have the classical cutting, grinding, polishing, electropolishing and ion milling, and also you can use focused ion beam. The main objective is to prepare thin electron transparent foils, and you can use these for typical microstructure morphology, phase identification and defect analysis in metallic samples. In ceramics, you can think of mechanical thinning, that is crushing, grinding by a mortar pestle or by a ball mill. And then if I'm using bulk ceramic, you have also dimpling, ion milling, FIB, and also dispersing the powder on a simple 3mm grit. So this is also done to achieve electron transparent thin specimens with minimal defects or damage. And most importantly, brittle materials require careful handling. Polymers, these are extremely beam sensitive. There are techniques like ultramicrotome, cryo-ultramicrotome, and also for some you do staining, solvent casting and so on. Polymers and biological specimens have similar specimen preparation methods. The primary intention here is to improve the contrast, and that is why you do staining. For example, people use some silicon oxide beads, and they are used as markers, and you also coat them with gold or something else, and you do some dose tests and so on. In thin films, which are primarily used in the semiconductor area and also in quantum material field now, you intend to prepare cross-section or plane view specimens, and then you also prepare them by ion milling or site-specific specimens with focused ion beam. The primary intention here is to look at the interfaces and how the defect structure influences the property of the thin film that is deposited or grown. If you think about powders or nanoparticles, you can use classical solvent dispersion, ultrasonication and drop casting and TEM grids. And most importantly, you want to have a good density of the particles on the grid. You don't want it too high nor too low. And more importantly, the medium that you use for suspension should not interfere with the illumination conditions of the microscope. That is, you do not want to have a hydrocarbon layer being deposited on top of the surface. It is extremely simple and widely used methodology for particulate samples. In biological specimen, you typically use fixation, embedding, ultramicrotomy. You use some kind of polymer resins, or in some cases aldehydes or formaldehyde kind of fixation, and then you can section these biological samples, and depending on how you're studying which kind of a material, you can also use cryo ultramicrotome, or there is a methodology called as vitrification, which we briefly touched upon, and these are preliminarily used for conventional imaging or also cryo TEM methods. And then when you look at two-dimensional materials, you either deposit them on a substrate, but you want them to be freestanding, so you want to do some kind of a grid transfer or exfoliation or drop casting. And in some rare cases where the two-dimensional materials are few layers, you also prepare them by focused ion beam as well. The whole intention here is again to preserve the thin structure and minimize the damage as much as possible. You also do not want to have contamination as a consequence of the transfer process. So the most important objective of specimen preparation in TEM is to tailor the material type to ensure electron transparency and also preserve the structure and reliable analysis. In fact, it should be tailor the methodology to prepare the specimen to ensure electron transparency. The thickness requirement is typically less than 100 nanometers and often less than 50 nanometer for high resolution work. For damage mitigation, you also have low dose imaging, cryo preparation, and also dose tests that you need to do for beam sensitive materials. For precision preparation, fib is increasingly used. There is also cryo fib now, where you are also using cryo fib to prepare beam sensitive biological samples also. So that is a snapshot of the specimen preparation methodologies that we saw. And then moving further, there are a host of interesting specimen holders. I briefly touched upon the kinds of holders and some of the applications showing in situ heating and kind of corrosion reactions in TEM. So typical specimen holders that are compatible with our microscopes here are the single tilt holder, the low background double tilt holder, which is shown here. This is the single tilt and this is the double tilt kind of a holder. And nowadays you can have holders with electrical feed through, and on this you can place a MEMS chip which looks like this. You can design the kind of the circuit you want to have and the kind of signal you want to implement to the sample, and based on the stimulus that you apply, you can modify the specimen. And while this is happening, you have electron transparent membranes here, and on top of this you carefully transfer the specimen either by transfer through exfoliation and the other wet deposition routes, or either by focused ion beam transfer or simply by drop casting. Once you successfully transfer the specimen here, you can also do real-time imaging in TEM. So that is about the overview of the broad area of microscopy and the construction of a microscope and how you enable basic holders and specimen preparation and everything and start doing experiments in the microscope. Moving on, we will look at some of the signals generated in TEM, and we will summarize the different imaging modes and the mechanisms that are involved in obtaining these images in the next part of this lecture. So if you look at the signals that are generated in a TEM, a host of signals are generated. Once a high energy electron beam is incident on the specimen, you have secondary electrons, backscattered electrons, Auger electrons, visible light, characteristic X-rays and so on, which are coming out. Broadly, you can classify these as the elastic signal or the inelastic signal. And from the elastic signal, you are largely looking at most of the imaging that is done in the TEM. imaging or diffraction, I should say. And from the inelastic signal that is coming, like the characteristic X-rays, the secondary electrons or the Auger electrons. Auger electrons are primarily fixed to SEM, but with the help of characteristic electrons and the inelastically scattered electrons, you can do kind of chemical fingerprinting and also understand the functional properties of a material. So, by using suitable detectors and from the mechanisms that we know related to the interaction phenomenon, depending on the angles of scattering and the physics involved in how the scattering process happens, you can have suitable detectors with which you can detect most of these signals and then get useful information from a material. If I look at the classification of scattering in TEM, I can classify scattering either on the nature of the interaction that is happening, assuming that you have a wave nature. In fact, I always say that you cannot separate the wave or the particulate nature or the dual nature of the electron, but for understanding, you simply look at it as either coherent or incoherent scattering, where the scattered electron wave is either in phase in coherent scattering or there is no direct phase relationship between the incident and the scattered waves. And based on the angle of scattering, you are either looking at the forward scattered or the backward scattered electrons, and 95% or maybe 97% or even higher signal that you obtain in a TEM as forward scattered electrons, and based on this most of our imaging theory is built. Then based on the energy of the scattering event, you can classify it either as elastic scattering or inelastic scattering. Primarily elastic scattering is used in conventional TEM imaging and diffraction, and inelastic scattering you almost use it for all kinds of analytical techniques, and based on the angles of scatter you are placing the appropriate detectors and you are recording the information in a microscope. Let us look at now a summary of what we learnt on imaging and diffraction in TEM, in particular the imaging modes and contrast mechanisms. Now let us draw a parallel with a classical convex lens and understand how a lens functions. If I place an object at the focal plane of the convex lens, the rays that travel through the lens go parallel and they all converge and form some kind of a pattern at the back focal plane. Mathematically, you can relate these through a Fourier transform, and further from the back focal plane, when an image is constructed at the imaging plane, there is another mathematical relation which is the inverse Fourier transform of the information that is recorded at the back focal plane. Now, why is this important? If I take an image as you see on the left here, and if you assume that this is the object, and if it is going through a lens, if I apply a Fourier transform, what I see here in the spatial domain where I can describe the features with x and y kind of coordinates, I can now display them with some kind of a radial coordinates through something called as the frequency and also the intensity here. If you look at it, these portions close to the central spot are called as low frequencies and these are actually called as high frequencies. Typically, you can say that all these are low frequency and the features here are high frequency. And for a lens which has a limited numerical aperture, the frequencies that a lens allows you to pass through at the back focal plane is what decides your lens resolution. And to understand this in more detail, first of all, we should remember that you can link these two through a Fourier transform, and then the image is an inverse Fourier transform of this kind of information at the back focal plane. Let us look at what the classical optics tells us about the propagation of light and diffraction from a point source when you are recording information through a kind of a slit or a double slit or a wide slit or through a circular aperture, and this helps you formulate the concepts of resolution and the formulation of the Rayleigh's criteria. So if you look at the various diffraction cases, if you have a Young's double slit, the key idea is you have two discrete sources, and as a consequence of the superposition of waves that is going through these sources, the outcome is proportional to the phase of the light that is actually scattered through, and you can relate it through some relation, and the information you record appears like a fringe pattern like this. When I have a single wide slit, I can think of it as a slit which is broken down to multiple infinitesimally small sources which propagate forward by the concept of Huygens wavelet and superposition of waves, and the intensity from a wide slit actually appears somewhat like this. If I look at how light propagates through a circular aperture, the wide slit kind of an approximation now, if it is applied to a circular kind of a slit which is wide enough, you do a two-dimensional integration and you get something called as the Bessel's function, and it appears like this. This is called as an Airy disk, and if I take a cross section of this, your intensity distribution is a function of the angle of scatter like this, and the first minima is given by this value. And if I have 2 point sources which are overlapping with intensities like this, the separation between either the full width at half maxima or the 80% height or 90% depth of the peak, you can define resolution, and typically for transmission electron microscope the accepted value is around 80% of the peak height, and this simplifies to 0.61 lambda over alpha or sine alpha. So this is what your resolution is in drawing parallels with classical optics. Now what you need to remember is, in a transmission electron microscope, by switching to electron source instead of light, you are lowering this wavelength here and you are improving the resolution. So moving on, the kind of information you record in a transmission electron microscope is intensity distribution. If I look at a table like this, here is some kind of ones and zeros, it is kind of a binary information. If I display this two-dimensional array as an image, this checkerboard pattern is what your image appears like. This is called as a bitmap image. Now, in transmission electron microscope, because the electrons naturally are far lower in wavelength than the visible light, there is obviously no color, and what information you record is simply the distribution of the intensity of the electrons that are recorded on a detector. You convert this to an electric signal, and if I display the image that is recorded in terms of a grayscale image, I can think of it as an array which looks like this. Here is a 32 cross 32 array of intensity distribution where the values of intensity range from 0 to 255, and a typical image that is recorded appears like this. Now the contrast variations you see in a material are typically like this in a transmission electron microscope. So remember, there is definitely some information regarding the material which you are trying to retrieve and correlate, but the imaging system that is used is displaying only intensity variations which are captured on a fluorescent screen or a CCD camera. And when it is this kind of a process, there can be artifacts which can often be misleading, and before you interpret the intensity variations with some kind of microstructural features, please try to understand why this intensity distribution happens and then correlate it with the knowledge you have on the material. That is when you can do a comprehensive analysis. Now, an important thing is these electrons which pass through the objective lens, they interfere and they form a kind of a spectral pattern at the back focal plane. And if I think of an object which appears like this, and if it is going through an objective lens, what I can do is I can dissociate this kind of a periodic repetitive pattern to sums of sinusoidal waves which appear like this. So what am I trying to achieve here is any image or any periodic pattern, you can break it down to sums of sines and cosines which appear like this. And if I write the amplitude and the phase value of these kind of repetitive patterns, the image which is shown on your left here can be decomposed to sum of 3 repetitive periodic patterns like this. So as you can see, if I take a horizontal cross section across these 3, my phase information is actually changing, which is proportional to what I see here, and the width of these or the frequency of these is changing when I look at the histogram on the x-axis. You can either represent it with a position vector k1 bar, or I can use it as summation of simply one kind of a sinusoidal wave with changing the wave front. So if I look at the mathematical notation of these 3 periodic repeating units, this is how it looks like. And why am I showing this is, any image you record in a transmission electron microscope can be decomposed into these kind of components, and when I take a Fourier transform of this, I can actually switch from the spatial domain here to the frequency domain here. And how does this appear? First, let me take a not periodic kind of an image and let me do a digital fast Fourier transform on this. Your frequencies appear like this, and I introduced you that when I have a lens or an aperture which limits the information at the back focal plane, that is when I am changing the resolution of an image. And if you see, if I use a low pass filter which is allowing only the low frequencies, this sharp edges which are visible reasonably good and these features which are appearing sort of focused will now become more blurred here. This is what your low pass filtering does, and this gives you an idea that your resolution of your imaging system is only as good as the higher order frequencies that your imaging system allows you to pass through. And if I do the opposite now, whereas I apply a high pass filter, the features which are really sharp and detrimental to the resolution of the microscope are all corresponding to the high frequencies. So if I look at the Fourier transform of this kind of a periodic pattern, I would see some bright spot like this, but I would also see reflections at distances like this, and this is proportional to my K1, K2 and K3 which I represented in this particular figure. So this kind of bridges the gap between the periodic patterns that you record in a high resolution image and the diffraction pattern and the diffractogram or the fast Fourier transform you obtain from a periodic repetitive structure that you record in a high resolution TEM micrograph. So this is some of the ideas on what your lens does and how the information is transferred through a microscope. Your microscope can be thought of as a mathematical operator. Your lens actually modulates the phase of the electron wave. Your sample also modulates the electron wave. There is something called as a projected potential, which you will see in the upcoming discussion on high resolution electron microscopy. And the features you record are dependent primarily on the spatial frequencies that your lens allows. Now if you recollect our discussion on electromagnetic lenses, these are highly defective because of the poor field distribution that you have, and as a consequence you are not allowing some of the higher order frequencies, and as a result you are limited in the resolution. Let us now look at the concept of imaging in conventional TEM. Here is an example of a bright field TEM micrograph. The dark features you see here are a secondary phase or a precipitate. The line you see here is a grain boundary, and the feature you see here is actually called as bend contours or diffraction contrast. This is in fact an example of a bent contour, and this is diffraction contrast due to this particular grain being close to the zone axis. What you are representing in this image is the distribution of amplitude over 2 dimensions that you are recording on the fluorescent screen or on your CCD camera. If I try to understand the contrast mechanisms in TEM, we have summarized them with these kind of details. Primarily, you have either the amplitude contrast or the phase contrast. In amplitude contrast, again, you have the mass or atomic number contrast. Then we had the thickness contrast. You have the diffraction contrast, and then you have the channeling contrast, which is also related to the diffraction contrast. Then you have the phase contrast, which arises from interference between the transmitted and the diffracted beams. This is what lays the foundation for the idea on high resolution imaging, where you are assuming or where you know that the atomic columns are acting as scattering centers, and the lattice fringes that you obtain, which is periodic, is actually kind of an interference pattern. In amplitude contrast, again, there is a lot of variation in the material, which is either due to the atomic number difference or the specimen thickness or the diffraction conditions, which generates this amplitude contrast. And I've broken down in detail in this particular slide here. So heavier atoms scatter electrons more stronger. We introduced the concepts of Rutherford scattering experiment and also defined the scattering cross section, which is defined as the probability of a successful scattering event. The differences in atomic mass and atomic numbers of the constituent elements gives you the atomic number contrast. The same thing in thickness contrast. Thicker regions tend to scatter more than the thinner regions, and this gives you a variation in the intensity of the specimen that you are imaging. And the contrast in case of diffraction contrast depends on how strongly the crystals are oriented or how they are satisfying the Bragg's condition with respect to the incident electron beam. This plays an effect on imaging defects, strain, and variations in the local diffraction conditions. For example, if you want to image dislocations or bent contours or grains and also stacking faults, your diffraction contrast becomes very important, and by using special illumination conditions, you can choose to highlight one of these diffraction spots and image the defects in a very successful way in transmission electron microscopes. Then we have channeling contrast. The channeling contrast in scanning electron microscope is primarily used for ECCI imaging, but in transmission electron microscope, you saw this kind of a case where a specimen close to the zone axis. So in this kind of a condition, you want to intentionally orient the specimen to obtain high resolution imaging, but you also, when you look at the larger field of view, the grains that are closer to the zone axis tend to appear darker. This is a consequence of channeling contrast. And then phase contrast, we will look at this in a little more detail when we see the summary of high resolution imaging. If I look at the common operational modes in conventional TEM, you have the incident beam, and after the interaction with the specimen, you have the direct beam or the electron beam, which is scattered at small angles. Typically, when your angle of scattering is satisfied by the Bragg condition, which is dependent on the crystallinity of the specimen, by either choosing the beams in and around the central beam or the direct beam, you can improve the contrast by inserting a diaphragm or the objective aperture, and by choosing the beam that is deviated at a specific angle of scatter as a consequence of the change in the diffraction conditions. This is actually a weaker beam than the central beam, so this is called as weak beam diffraction conditions, which is then used to image and obtain what is called as a dark field image. So here is an example of a specimen which is being recorded by allowing all the forward scattered electrons. In this case, if I now put in an aperture and allow only the central spots which are highlighted here, in fact some of these spots are missing in this, my contrast actually improves slightly, and if I use an even smaller aperture, my contrast changes. Now remember, the resolution is again dependent on the spatial frequencies that I am allowing at the back focal plane. So you are actually gaining the contrast. If I look at the histograms across these three features on this image, the difference between the brightest and the darkest regions is prominently more here than here. The slope is slightly changing than over here. So you improve the contrast, but you also lower the resolution a bit. So once you orient the specimen in the zone axis and you want to obtain high resolution imaging, you do not want to use any of the apertures to block the higher order frequencies to obtain a very good high resolution image. But when my intention is to image defects or to improve the contrast of the features that I want to see, then I intentionally use an aperture, and this is called as switching between the bright field and dark field images. The image shown on left is a bright field image from precipitates which are on the surface of an aluminum sample, and the image on right is by highlighting one of the weaker beams or the diffracted beams, and you can see the defects here and the bend contours more prominent. In fact, these are kind of the fringes that are caused as a consequence of variations in the diffraction conditions here within the specimen. So bright field and dark field imaging is the most basic conventional imaging that you see in any transmission electron microscope, and this is the most used technique. And the primary mechanism of the contrast that you get in bright field and dark field imaging is due to the amplitude contrast, which in turn depends on the mass thickness and the diffraction contrast. Then we mentioned that when the parallel electron beams that are passing through a specimen go through the objective lens, they all form an array of spots at the back focal plane, and here is an array of spots that you can see from a crystalline material, a single crystal, which is oriented along a crystallographic zone axis, and you can see that the intensity of the central bright spot is the highest, whereas the intensity dies down as I go farther away from the central beam. This is also what you see from an aperture, because you are using the illumination by using circular apertures which are restricting the path of the electron beam. The intensity naturally dies out as you go farther away from the central beam. And by orienting the specimen in specific zone axis conditions, I will not go into the details of zone axis orienting the specimen. We have seen the demonstration of these, and we have also seen some basics on crystallography of how the indexing of these diffraction patterns is done and how the orientation is done. Let us try to understand how these diffraction patterns are obtained in TEM. So if I look at this reference image again, where I see the microscope column and the schematic of the column, when parallel electron beam which is illuminating the specimen is imaged such that the specimen is also oriented along the crystallographic zone axis. That means if here is my unit cell within a crystalline specimen that is being imaged, if I orient the grains or the crystal in a direction such that one of the crystallographic planes is actually parallel to the electron beam, in this condition I am actually satisfying the Bragg's law. For the electron beams in the microscope, the angle of scattering is extremely small, of the order of 10 to 20 milliradians, or typically less than 3 degrees. So as a consequence, all my planes which are oriented parallel to the electron beam would satisfy my Bragg diffraction condition, and when parallel beams go through an objective lens, they all converge at the back focal plane. Now, when I use the back focal plane as the object plane for the illumination lenses, I record the diffraction pattern. When I use the image plane of the objective lens as the object for the illumination lenses, what I record is the image. And we also established some time ago that this periodicity which is observed at the back focal plane can be related to the information within a specimen or the periodicity within a specimen through the Fourier transform, and the information I record from the image plane is an inverse Fourier transform of the information at the back focal plane. So this is what happens in an electron diffraction pattern. And if I look at an electron diffraction pattern, the distances in diffraction pattern correspond to the angles of scatter. The most intense beam is at the center, and the scattering intensity decreases with increasing angle of scatter. The intensity varies strongly within the specimen, and there are specific methodologies with which I can start indexing these reciprocal lattice vectors, and from this I get the crystallographic information on the specimen. When I talk about solving the crystal structure and obtaining crystallographic information, I would say transmission electron microscope is extremely important to understand the symmetry, the positions of the atom and the crystal structure information, but it is a very localized technique. Often complementing this with an X-ray diffraction study gives you the complete information on crystallography from a material. So when I define the crystal structure problem for any unknown material, you have to determine three parameters. Primarily, you have to determine the cell parameters which give you the lattice spacings. That is, when you define the Bravais lattice, you define the unit cell vectors in A, B and C directions. That is what you obtain from spot diffraction pattern when you are illuminating in a parallel beam mode. Then when I converge the beam and I record sort of disk patterns, I get the information on the symmetry from an electron diffraction pattern, and this is often recorded as what is called as a convergent beam electron diffraction. In this course, we only focused primarily on the spot patterns or obtaining electron diffraction patterns with parallel illumination. The determination of space groups and understanding convergent beam electron diffraction pattern is an advanced module, and once you are conversant and familiar with conventional diffraction and imaging, this becomes a natural next step and you can always take that leap. And next, the third important parameter is understanding where my atoms are sitting within a crystalline unit cell. Unless you've determined all three of these parameters together, you would not have solved a crystal structure. So I'll just recollect how we've demonstrated that you can use simple tilting and parallel illumination in a basic conventional TEM to get the crystal structure information from a specimen. If you have a specimen which is oriented in this kind of a condition, and let us say there is a set of planes which are satisfying this parallel illumination with the electron beam, these planes give me some kind of diffraction pattern which is corresponding to this distance is here. So if I call this as G1, so if I call this as D1, the reciprocal vector G1 corresponds to this distance, and this distance you see here now corresponds to this distance. In fact, this separation here is larger and this separation is actually smaller. So you can say that this is G1 now and this is G2, or this can be D2, where G2 and G1 correspond to the reciprocal lattice vectors of these planes D1 and D2. If I now use one of the crystallographic axes as constant and I now tilt the specimen in this direction, I obtain the planes with varying G1 and this G2 remains constant, and with these variations, whatever projections I record, I can overlay them over each other and measure them and plot them on a kind of a graph paper and see with how much angle of deviation, how these diffraction spots are changing, and I can construct the projection of a reciprocal unit cell. So this helps you determine the unit cell parameters very accurately, and once you know this, you can also get information on the symmetry either by corresponding X-ray diffraction pattern and by using Rietveld refinement methods, or by using convergent beam electron diffraction techniques and determine the symmetry, and then you would have solved the crystal structure to an extent. And then once you determine the space group through focus exit wave reconstruction imaging by high resolution electron microscopy, you can completely solve the crystal structure. So at this point, we will now move into the next methodology of imaging that we learned, which is high resolution imaging in TEM. So if you look at an example high resolution micrograph from an uncorrected microscope, what you see here is a periodic pattern. Remember, this is not an image of the atoms, but it is an image of the atomic columns, and this is a high resolution image of the lattice fringes. Do not assume that these are actually individual atoms, but these are atom columns, or this is called as lattice fringes, and the periodicity you see here is a consequence of the periodic arrangement of atoms within a crystalline lattice. And if you consider each of the atomic columns are actually acting as sources to deviate my electron beam, and if I think of them as periodic sources arranged in a periodic manner, what I record here is sort of an interference pattern. I am overly simplifying this concept, but let us understand how high resolution imaging is done. So primarily you have to check the diffraction pattern and orient the crystal into the zone axis. We discussed this in the demonstration sessions, and once you orient it into the crystallographic zone axis and do all the primary corrections, you can then start imaging and get information on the high resolution from that particular material. So where do we start this? If you think of an isolated atom, the atom actually has an inherent potential associated with it. So as the electron wave travels across the distance of the atom, it accumulates a certain phase, and this actually, if you compare it with the refractive index for light, you can substitute the refractive index with the phase modulation or the phase shift that is caused by an isolated atom, and what you then get is actually called as the projected potential. So the phase modulation by an isolated atom to the charged electron is what causes the deviation of the electron beams, and from an isolated atom you can understand the phase shift is written in terms of the projected potential of an atom. Now when I take this and extend it and build it to a crystalline sample, you can start with the simplest case where you have two simple atoms, and when you superposition these exit waves from these two, the contrast then depends on the atomic separation. This can be bridged with the classical Young's double slit experiment that you learnt, and the spatial frequencies are transferred by the lens. This also directly connects to your electron diffraction theory. If I consider the exit wave as an expansion like this, when I write a polynomial expansion for the exit wave in terms of the phase, this is actually a complex number which can be expanded. If you take what is called as the phase object approximation, in understanding the contrast variations in high resolution electron microscopy, a concept called as phase object approximation has been introduced. So the electron wave that interacts with the specimen modulates the phase of the incoming electron beam, and in terms of the spatial positions of the atoms that are sitting within a crystal, you are varying the electron phase, and you can relate this phase to the potential associated with the positions of the atoms which are sitting in two dimensions. The third dimension of the thickness has been ignored in this particular equation that is shown here. When you take really thin objects, you can always use this kind of an approximation, and this is called as a weak phase object approximation. And when I look at the Fourier transform or the Fourier space of the information that is recorded at the back focal plane, you can write it in terms of the reciprocal lattice vectors as this. So, the interference of two atoms, this can be expanded further, and you build the concept of projected potential and modulation of this projected potential by the electron lenses, and as a result you get the high resolution phase contrast images. So, where does this contrast come from? The objective lens introduces a phase shift, and this depends on the spatial frequency, that is what we saw here. So, if I have an objective lens like this, the change in the focus can introduce some change in the frequency, and the positions of the atoms can also introduce the change in the phase. So, what I then get is, with a lens, there is something called as the aberration function. So, the phase change just by a lens alone without introducing a periodic crystalline sample can be expressed in terms of an expression like this. So, this chi is called as your aberration phase function. It is actually a complex number, and u and v are the spatial frequencies, and the phase modulation can be written in terms of this aberration function. So, if I look at how the phase shift happens, it is given by this equation, and if I look at the real part of this expression, and when you do the polynomial expansion, you can take the real part as almost equivalent to 1. So, there is hardly any amplitude change as a consequence of the constant phase object, but when you look at the reciprocal part, when you look at the imaginary part, which is the sinusoidal of chi of uv, this gives me what is called as the contrast transfer function. So, if I use this expression in this kind of an exponential term and look at the complex function, you can think of lens as a spatial frequency dependent phase plate, and it strongly depends on the spherical aberration, the defocus, and the electron wavelength. Now, this information from a lens convoluted with the projected potential from the crystalline sample is what is recorded in an image in a high resolution micrograph. So, let us look at this contrast transfer function and recollect this. If you take the aberration function and you take the differential of it and look where it reaches a maxima, at a negative defocus you can counter the spherical aberration and you can get sort of a maximum intensity, and this is called as the Scherzer defocus. And when I look at the phase contrast that is obtained from these kind of images, this is analogous to the Zernicke phase contrast in optical microscopy. The sinusoidal part of the contrast transfer function of the lens transfer function appears like this, and this point of intersection is what is called as your point resolution, and as you go farther away these frequencies get damped, and the end of where these frequencies are completely damped, that is called as the information limit. And by changing the defocus and also depending on the thickness of the specimen, the intensity that you record or the phase shift that is caused actually is what gives you the contrast in the high resolution micrographs. So, if I summarize all of these and bridge them together, if I look at the imaging system in a transmission electron microscope, the specimen itself has a projected potential, and when the electron beam goes through this, inherently you are introducing a phase shift due to the projected potential, and when this is now modulated by the impulse response function of the microscope system, and if I record the information, what I record in an image is a convolution between the object function, which is inherently a convolution between the projected potential and the lens aberrations, and this convoluted with the impulse response function is what I am recording in an image. And if I look at what I record at the back focal plane, it is related to this information through a Fourier transform, and what I record at the image plane is again an inverse Fourier transform of this. So, from all these you can summarize the information you record for an exit wave is given by a function like this, which is strongly dependent on the thickness, the defocus and the lens aberrations. And by minimizing the spherical aberration and chromatic aberrations, your aberration corrector actually breaks the resolution barrier. This is imaging by looking at parallel illumination, whether it is bright field, dark field or high resolution imaging. Now let us see what happens when you converge the electron beam to a probe and record the information by rastering the electron beam over the specimen and collect the forward scattered electrons on a detector. So this is called as imaging in STEM mode. So you form a probe here, and typically by using special apertures here, you are limiting and restricting the aberrations that are formed on the probe when you converge the beam here. And by choosing only the central beam that is converging to a very sharp point, you raster this onto the specimen and you record the image. The forward scattered electron, like in case of the bright field and the dark field imaging, is scattered through various angles. And if I look at the rastered image from left to right, when you raster, the features that are showing you a difference in the atomic number or the thickness will naturally give you a variation in the contrast. And this image on the left is recorded by collecting the signal which is scattered at a slightly higher angle. And if I look at this from the top view, the configuration is the bright field detector is somewhere at the center where I am collecting the forward scattered information closest to the principal axis, and by using an annular dark field detector, I am collecting the radial information which is scattered at a slightly larger angle. And if I understand the contrast mechanism by taking an area integral over this kind of a detector, when the probe interacts with the specimen, your exit wave can be written in terms of the radial coordinates like this. So the specimen modifies the amplitude and the phase locally. The transmission depends on the atomic structure. In a STEM, when the probe position moves, so if this position vector is changing, this is how my position vector changes. And when I look at the measured intensity, the intensity as a function of the position change can be integrated over a solid angle which is recorded onto the detector as a square of this exit wave. So this is what your amplitude is, and when you look at this, for small angles you record the bright field image, and for large angles you record the annular dark field image, and this is how my detector positions are. For very large angles, this intensity that you record is actually proportional to the atomic number to the square root of 3, or it is approximately z square, and this is called as high angle annular dark field image. If you look at the scattering angles in a transmission electron microscope, primarily the bright field and the annular dark field detector is still in the regime where you are recording the diffraction contrast information. You intentionally want to record for very small camera lens and with very large collection angles in such a way that the area integral of this intensity is predominantly dependent on the atomic number, and in this configuration you record what is called as a high angle annular dark field image, and this gives you what is called as Z contrast in STEM mode. So while you are imaging in STEM mode, by using a high angle annular dark field detector, you can visualize the exact positions of the atoms, and the intensity that you record is now strongly dependent on the atomic number. So typically the images collected with the elastically scattered beams at higher angles show a strong dependency, and this is an annular dark field image which simply shows you the variation of intensity as a consequence of a change in the atomic number, whereas here this is an HADF high resolution STEM image that is recorded, and you can see that the atomic number when I take the intensities is proportional to the intensity of the image when I take across this planes is proportional to the atomic number of the atoms that are positioned here. So this is what you get in a STEM imaging mode. This STEM mode of imaging is extremely interesting and important for analytical studies when you want to relate the raster, and from each of the positions when I collect the analytical signal corresponding to the characteristic X-rays or the forward scattered inelastic electrons as well, and this gives you a wealth of information from a specimen. So after understanding all of these imaging modes, we've moved on to the example of inelastic signals, and we've seen two cases of recording EDS maps and also some introduction to electron energy loss spectroscopy. If I look at the signals in the conventional TEM again, you have elastic signals and inelastic signals, and inelastic signals are the ones which have lost energy after interaction with the specimen, and from the inelastic signal you are actually getting analytical information from a specimen in a microscope. So inelastic scattering, how does this happen? When the electron beam hits the specimen, the high energy electron beam must penetrate through the conduction and the valence bands of the specimen, and it interacts with the core electrons. And when a critical amount of energy is transferred to the inner shell, you create a kind of a hole, and there is also the generation of secondary electrons during this process. And as a consequence of this creation of holes, you can have intra-band transitions, and as a consequence of this, you can have emission of a characteristic X-ray or an Auger electron. And if I look at the Bohr's model of the atom, this is how the electron shells look like, and from the Rydberg constant and the Bohr's model, you can actually exactly calculate what are the energies associated with each of these transitions, and it is strongly dependent on the atomic number. So for every atom, when you measure the energy of the inelastic event that is associated with each of these transitions, you can get to know what kind of valency, what kind of element is present, and this helps you understand the compositions of a material. So when you look at this, I have just summarized all of this in the discussion now. So because of the transformation within the atom, because of the transition within the atom, you actually have emission of characteristic inelastic signal, and by using appropriate detectors, you can understand what material is present or what atoms are present inside a specimen. One of them is, of course, looking at the characteristic X-rays. Characteristic X-rays are often called lines because in the older generation spectrometers, you were recording them as lines on photographic plates. Each X-ray line has a specific characteristic energy. Typically, this is within the range of 0 to 20 kilo electron volts or 0 to 40 kilo electron volts. And if you look at the area under the peaks of each of these characteristic lines, and if you look at the relative proportions of the equivalent weights that are proportionate to these intensities, you can use this through a simple proportionality relationship, and whether they are coming from which kind of a shell from a specific atom, you can quantify, and this is actually called as quantitative EDS mapping or EDS spot analysis. So when a group of X-ray lines are originating from a particular shell, you call them as the K family, L family or L family lines, and typically you can quantify from these peaks through what is called as the Cliff-Lorimer equation. So if A and B are two atoms that are giving me characteristic X-ray lines with intensities IA and IB, this is specifically looking at the area under these peaks. You can relate the equivalent weights proportionate to the area under the intensities that you record, and from these weight fractions you can actually quantify how much amount of which element is present. And this is typically used in the EDS analysis that you do. And talking about the other inelastic processes, we've covered the electron energy loss spectroscopy in particular. You also have the generation of secondary electrons, Auger electrons, electron hole pairs and cathodoluminescence. The interband and intraband transitions, you can actually study them and you can link them to the valence band and conduction band transitions. This is typically the low loss spectra that you record in electron energy loss spectroscopy. You can get the information on the bonding between the atoms, the valency and so on. So this is a wealth of information that you can record from the process called as electron energy loss spectroscopy. Electron energy loss spectroscopy requires a special kind of construction. In our detailed discussion, we've looked at the construction of what is called as an omega filter, or we've also seen the post-column Eales filter, which typically consists of a magnetic prism where you're separating the electrons to different energies, and based on this dispersion, you get a wealth of information from a material. So this is how a typical signal in Eales looks like. I have the zero loss peak, and then I have what is called as the core loss spectra. And when you look at the ionization edges, this is what consists of the information that you get from the bonding or the valency from different elements. So typically this is recorded over a range of 0 to 3000 electron volts, and this covers most of the elements, and typically Eales is extremely sensitive to low atomic weight number materials. You can also measure the thickness of the specimen from the bulk plasmon peaks, and with a very high resolution Eales spectrometer, you can also get information on surface plasmons and so on. So if I look at an example Eales spectrum, this is how it looks like, and if I look at it more closely, here is an ionization edge from aluminum. Bear in mind the strong background intensity is because of the thickness of the specimen, and depending on how I change the dispersion of the spectrometer, I can specifically choose a channel of energy and then get spectra from that particular region. The spectrum you record in Eales is analogous to the spectrum you also record in XPS, but in Eales you also have the local position and the microstructural information as well as the electron energy loss spectrum. So this makes it a very powerful technique. So if I give you an example of another ionization edge, this is where you do not have the background subtraction yet, but when I fit in something for the background, I can actually see the oxygen spectra and the manganese spectra, and I can see the ionization edges more clearly. And from the shape of the ionization edges and the width of these ionization edges, I can actually get to know a lot of information about the material. And next, if I place some kind of a window and record the pre-edge and the post-edge spectra, and I only filter these out and record only the information around the specific ionization edge, I can get what is called as energy filtered transmission electron micrographs, and this is how your energy filtered TEM maps look like. And from each specific position, if I record Eales spectra like this, I can also get parallel Eales recording coupled with STEM. So this is called as STEM Eales, and people call this as either PEELS or STEM Eales electron spectral imaging. And with this, with a very good spatial resolution, you can also get the spectral information from each of the pixel where your electron beam is rastering through. So this is about the analytical signals you get in a transmission electron microscope. And finally, before we move on to the last concept that we learned on aberration correction, we also need to refresh our memory on the damage that is caused by the electron beam. Commonly, you have the radiolysis or the knock-on damage or heating, and in radiolysis, when the incoming electron beam actually causes an ionization of the atom where you are breaking the chemical bond. This is predominantly observed in liquids, ionic samples, and also even biological samples. You have the reaction products as a consequence of electron beam interaction, and you are kind of damaging the specimen. In the next case, which is knock-on damage or sputtering or even displacement damage, what happens is when the momentum of the incoming electron beam is transferred such that it can exceed the binding energy of a crystalline lattice. This is when the complete momentum transfer from the electron beam happens to kick out a nucleus from the crystalline lattice. This is where you have to overcome the threshold of the binding energy, and this is typically a 1 in a million probability, but it still happens more often over repetitive events. Such a damage is called as knock-on damage or sputtering. This is also observed in all kinds of specimens, and it is also dependent on the accelerating voltage. The radiolysis and ionization kind of a damage is more pronounced at slightly lower accelerating voltages, whereas when I go to very high voltages, the knock-on damage is more pronounced. So you have to have a good balance between the accelerating voltage and the dose that is deposited on your specimen. And another indirect consequence of the electron beam interaction with the specimen is the generation of phonons, which are the lattice vibrations which actually cause heating of the specimen, and this is more pronounced for biological samples and typically in metallic samples, which are also good conductors of heat and electricity. This is dissipated and you do not have significant heating, but as a consequence of this, you might actually damage polymers or biological specimens, and therefore you are imaging them at very low temperatures or cryo conditions, and this is what you have in beam damage. And finally, we looked at the concept of aberration correction. We defined aberration correction as not some kind of a special rectification of the complete electron lens, but more or less like wavefront engineering, and we drew parallels of aberration correction in optical lenses to the electron lenses, and we looked at the lens aberration function, and we saw the Zernike expansion of aberrations as polynomials, and how the Scherzer theorem tells you that it is difficult to correct the aberration for round electromagnetic lenses. So if you look at the aberrations in optical lenses, in an ideal case, you would assume that all the rays that propagate through a lens would coincide at a point, and in reality that does not happen. You have the meridional and the sagittal rays which are not converging at a point, and instead they converge at a disc or an ellipsoid. And in an ideal situation, when you have a paraxial approximation, the angles are really small, the rays are close to the axis, so you do not have a radial component, and it is kind of a perfect imaging condition. But if you look at reality, the rays have a finite angle and they do not converge at a single point, and there is a deviation from the ideal Gaussian imaging, and you call this as an aberration. This aberration can be described in terms of what is called as a wavefront error, and that is what we saw. You can expand the aberration of the non-coincidence of the wavefront to a single point in terms of some kind of a polynomial here in terms of the scattering angle and the radial coordinate, and this coefficient is what defines your aberration. And in terms of the scattering angle alpha and the distance from the radial separation, you can have terms such as alpha r square or alpha cube or r cube or alpha square r. All these together constitute the basic aberrations in optical lenses, which are also described as the Seidel aberrations. So alpha is your aperture angle here and r is the field coordinate, and any complicated wavefront can be built when you give an expansion to this aberration function in terms of the Zernike circle polynomials. if you look at the 5 classic Seidel aberrations, they modulate the wavefront in these kind of forms. And if you look at any classic textbooks on optics, you might have seen these kind of lens distortions or aberrations. You call them as spherical aberration, coma, astigmatism, field curvature and distortion. And each of these can be written in terms of the polynomials. For example, this being alpha cube and astigmatism and coma in terms of alpha square r and alpha r square and so on. And from these you can get to know that correction of aberration is actually modulating the wavefront and compensating for these kind of distortions of the wavefront. In classical optics, you are having very good experience in correcting the curvatures or by using combinations of lenses, and the rectification of optical lens aberrations is done as a standard procedure. But in electron microscopes, there is a serious limitation, that is when you have circular lenses, when you have radial or round electromagnetic lenses, because your Laplace equation of the potential has to be satisfied, and if you solve that, you would see that always you would have a positive CS value, and this is what your Scherzer's theorem states. So to overcome this, the breakthrough that happened is you have to break this symmetry and introduce some kind of ways to modulate the wavefront by introducing multiple lenses. And in this effort, there were attempts made especially by the groups from CEOs from the University of Ulm and Darmstadt and Jülich, where they worked on the hexapole kind of a construction to minimize the spherical aberration correction, and the group from Arizona State University of Professor Andrei Krivanek and Nick Delby, together they were looking at the octupole quadrupole combination. With this, the idea of stacking electromagnetic lenses telescopically one over the other was thought about, and by minimizing the engineering defects and with the feedback controls, what people have achieved is the breaking of symmetry of the round electromagnetic lenses and the compensation of the field and introduction of a negative CS, because the round electromagnetic lenses always give you a positive CS, and by combination of these hexapole or dipole, hexapole or quadrupole and octupole kind of combinations, you can look at the analogies to the Zernicke mode and TEM aberrations, and by engineering the wavefront, you are actually compensating the, or you are balancing out the electromagnetic fields to compensate for the wavefront distortions. And the larger distortion free region you have here, the radial component of this gives you a better resolution. And nowadays with this, people have achieved resolutions as low as even 0.5 angstroms, or even, if I am not wrong, 0.3 angstrom, and we are at the ideal limit of aberrations as on today. So by correcting spherical and chromatic aberration, we have pushed the boundary of resolution limit in transmission electron microscopes, and this is what you have in most of the modern day microscopes now. Just briefly refreshing your memory on hexapole correction, there are combination of 2 hexapoles with 2 transfer doublets in between. The hexapole initially introduces second order and third order distortions and aberration, and the transfer doublet images the first hexapole onto the second with a magnification of -1, and the second hexapole cancels out the second order aberrations, and you are left with only the third order spherical aberration, and this is in a negative value. This negative CS now cancels out the positive CS of the round electromagnetic lens, and this is how you correct for the spherical aberration with a hexapole kind of a corrector. Then when you have the quadrupole octupole corrector, you have a symmetric design where you have a combination of the octopoles and quadrupoles, and even in this, by introducing the double symmetry, you are cancelling out the coma, distortions and two-fold aberrations. When you do an anti-symmetric excitation, you are cancelling unwanted multipole effects, and ultimately with the octopoles, you are controlling the third order fields and you are introducing a negative CS again. The advantage of this quadrupole octopole kind of a construction is you can also have crossed electric plus magnetic quadrupoles, and the electric component here acts as a first order Wien filter, and this also acts as something called as a chromatic aberration corrector. So what happens is, if one of these one of the quadrupoles, if I am replacing with the electric component, for any small distortion in the incoming electron wavefront, if there is any gradient in the energy, the faster moving electrons bend more inward and the slower moving electrons bend more outward, and you are now kind of compensating for the chromatic spread, and with this kind of a construction you can also have chromatic aberration correction as well. So with this you break the 1 angstrom resolution barrier and you achieve very good resolution, and with the feedback control and the very good electronic stability of these components, it has become more or less a standard practice these days with installations of electron microscopes with both spherical, and there are very few installations of chromatic aberration correction as well. And this quadrupole octopole kind of a corrector is very commonly found for the neon systems, which are exceptional for spectroscopy studies as well. So with this, I hope I've summarized all the lectures and all the concepts that we covered. I'm sure this must have been quite loaded, but this will just give you some kind of information on a kind of a flow on the structure of the course and a brief recap on what has been covered. So with this, I'll end this discussion here. Thank you, and I hope you find this content useful, and maybe it helps you go one step further and gain better understanding when you're doing microscopy practically. Thank you very much.